Yeah, in English, in English.
In English, okay. So good afternoon to everybody. It's really a pleasure to be remotely here in this to come to know a little bit more about Juliana, Professor Juliana Vizzotto's work. She's a professor from Universidade Federal de Santa Maria, in the very south of Brazil. And she is going to present a very interesting work about a new language for quantum computing, which I think it's the way to move forward in quantum computation, because this way we can take the programs to the level of conventional computing programming. And maybe we will enhance, we have a better performance in time and in the computational time. So, Juliana, please.
Okay.
You can share your screen.
Okay.
Okay.
Can you see? It's okay?
Yes.
Yes, yes.
Okay. So thank you very much, Priscilla. And first of all, I would like to thank the QCTalk organizers for the invitation to talk about my work on quantum computing, more specifically about quantum programming languages. So I'm very happy to be here today. I'm present here today, a joint work with Amer Sabri from Indiana University and Benoit Valiron from University of Paris Sud. So this is my roadmap, and basically in this work, we define a purely quantum programming language, including some notions of quantum control. The structure of control flow in classical programming is well understood. However, in quantum programming, it is still a new and intricate subject, and our language is essentially motivated by the notion of symmetric pattern matching. So I'm going to start to talk about quantum control, and for that, I'm going to discuss the models of quantum computation we can consider, and the notion of control in quantum programming. Then I'm going to mention some previous approaches in the context of quantum control paradigm. And finally, I will show our approach based on pattern matching isomorphisms. So from one point of view, the quantum algorithms can be considered as classical algorithms having access to a quantum memory. So we have the classical computer, and we have this quantum memory that holds on only quantum data. So considering this perspective, the control flow notions of sequencing, conditionals, loops, and recursion are classical. And a quantum program can be seen as the construction, manipulation, and evaluation of quantum circuits. So I'm starting with some preliminary concepts. So the quantum memory has qubits, and a quantum memory with any quantum bits is a complex combination of strings of any bits in a Hilbert space. And here I have an example of a quantum memory with 3 qubit states. and we have a normal condition. It's a superposition. Here is a superposition, and we have a normal condition. And unlike probabilistic distributions, all are available at the same time. Here I have the first qubit, the second qubit, and the third qubit. So the stream of instruction on the quantum circuit model is given by a series of elementary gates applied on the quantum memory. And here the wires indicate the quantum bits, the quantum memory, and the gates are unitary and reversible. And there is no quantum loop, no conditional escape or branching point. We can have circuit combinators used to build complex circuits for repetition, inversion, and the control. The controlled circuit. This is the conditional action of a circuit. Here there is an example, and we have the qubit 1 acting as the control, and C is applied on the qubits 2 to 4 when 1 is true. And suppose that C flips its input bits, then the above circuit does, if the control is 1, then we'll flip the qubits 2 to 4. And if the control is 0, nothing happens. And this is the example as the quantum test that we will formalize as well. So the control flow of the program is on the classical computer, and it generates the quantum circuit that will be executed on the quantum memory. So the idea in the quantum control paradigm is to work the notion of control flow that itself quantum. So we move control inside the quantum memory. So there is distinct behavior on each different state in the superposition. There is the notion of quantum test, the quantum if, and the notion of quantum loops or fixed points. So quantum control is a long-term objective. So we just start to work with. So the idea is to understand the structure of quantum operations and to have a syntax for building circuit combinators. Challenges, there is the preservation of unitary, that is norm and orthogonality of states. Here is just an example of a quantum if, and we need to guarantee orthogonality of the branches and norm conditions. Quantum termination, and unlike probabilistic behavior, our branches are available. And as measure of success for capturing quantum control, we can consider the compilation of the language to quantum circuits and to model the constructions as unitary in some Hilbert space. So here as this works, we based a lot in previous approach. So I'm bringing here some previous works and some points that we want to deal in our proposal. And so here there is the work QML. And here what we want concrete syntax, we want recursive types, higher order, or talking about high level programming. So we want orthogonality and norm, quantum tests, quantum loops. So here QML, This is a work of a pure quantum functional language. It has the construction, it has quantum control, it has a if, quantum if, and here there is a concrete syntax, it takes care of orthogonality and norm and quantum test. This is the work by Altenkirch and Gratage. There is the quantum lambda calculus by Van Tonder. There is a concrete syntax, higher order, orthogonality and norm. The linear algebraic lambda-calculi by Ahig-Dweck. There is concrete syntax, recursive types and higher order, quantum tests, quantum loops. The INGS quantum loops, orthogonality and norm, quantum tests, quantum loops, and the circuit description languages, the Kuiper and Quirire, concrete syntax, recursive types, and higher order. And so we want to deal with all these topics in our proposal. And of course, we based a lot on these previous works. So considering quantum control flow, quantum tests are quite fine. They can be done with regular control, quantum if, and quantum loops are the main roadblock. Inspired in linear algebraic lambda calculus that has an expressive language, ING's approach, satisfactory loops, and KML, preservation of unitary. And our proposal tries to reconciliate these features. So I'm starting to talk about pattern matching and quantum control. So the most elementary control structure in a programming language is the ability of conditionally execute one of several possible code fragments. However, expressing such abstraction using predicates and nested if expressions makes it difficult for both humans and compilers to reason about the control flow structure. Then, instead, in modern functional programming languages, the conditional control flow is elegantly expressed using pattern matching. And this approach yields code that's not only concise and readable, but also enables the compiler to easily verify the following two crucial properties that are non-overlapping patterns and exhaustive coverage of a data type using a collection of patterns. Indeed, most compilers for functional languages perform these checks, warning the user when they are violated. And at a more fundamental level, like in type theories and proof assistance, these properties are actually necessary for correct reasoning about programs. So our first insight in this work is that these properties are sufficient to produce a simple and intuitive first-order reversible language. And here there is an example written Haskell-like. Haskell is a classical functional programming language, Haskell-like syntax. We start with an skeleton of a function that accepts values of type Natch plus Natch. The patterns on the left side are exhaustively covered. They exhaustively cover every possible incoming value and are non-overlapping. And the function G accepts a value of type bool times Natch. And again, the patterns are of the left-hand side are exhaustively cover every possible incoming value and are non-overlapping. Then we claim that since types Natch plus Natch and bool times bool are isomorphic, we can combine the patterns of F and G into a symmetric pattern matching clauses to produce the function H. And here we show the function combine the clauses of F and G. And this is a reversible function that is obtained by simply combining the non-overlapping exhaustive patterns of the two sides of the clauses. And here we use the double arrow to show that is an isomorphism. And in order to be well formed in either direction, these clauses are subject to the constraint that each variable occurring in one side must occur exactly on the other side. And this work is this part of work is essentially based on a previous works by James and Sabri. And so the conditions for the reversible maps, the isos, are exhaustivity and overlapping. Here I have the formalization of the ideas present in the example. Not taking out of the time. So the language is two-layered. The first layer contains values, which also play the role of patterns. These values are constructed from variables ranged over X, and the introduction of forms for finite types A and B, constructed from the unit type, sums, and prod types. So the second layer contains collections of pattern matching clauses here, denoting isomorphisms of type A double arrow B. And computations are chained applications of isomorphisms to values. The typing rules are defined using two judgments for typing values, this one, and or patterns and terms, and with W for typing collections of patterns matching clauses denoting an isomorphism. The most interesting rule is this one, the only one that I'm showing here. For the isomorphism, and the rule relies on two auxiliary conditions. These conditions are the orthogonality judgment here, that formalizes that the patterns must be non-overlapping. So we captured these characteristics with the orthogonality judgment. And the condition D, which formalizes that pattern are exhaustive. The semantics is an operational semantics on terms using the natural notion of matching. And because the condition on patterns, the rewrite system is deterministic. And we can swap the two sides of our pattern matching clauses in an isomorphism. So the language explained so far embodies symmetric pattern matching clauses as its core notion of control, and its expressiveness is limited, however. So it's possible to extend it to have more common with conventional functional languages. So we extend the language with the ability to parametrically manipulate isomorphisms with a recursive type here, lists, and with recursion. the variable f expands the set of isovariables, and the variable x expands the set of term variables. We extend the layer of isos, here the layer of isos, so that we can we allow higher order functions and higher order manipulation of isos and isovariables and applications. So isos can be used inside other isos using the let construction. So here we have some examples. We can encode booleans as usual, using the type plus 1 plus 1, and true as left, and false as right. So we can define the function not, which flips the boolean easily using an iso. So it's defining just this way using symmetric pattern matching, which is non-overlapping and exhaustive on the domain. So we can define the controlled not gate with the controlled not gate, which flips the second bit when the first is true. So and by using the abstraction facilities in the language, we can define higher order operations that build complex reversible functions from simple ones. For example, we can define a conditional expression parameterized by the functions used in the two branches. So here we have if parameterized by g and h. So using if and the obvious definition of identity, we can define the control as control f, control as control f if fid. And recover an alternative definition of C not as control C as control not. So we are having like a more high level constructions in the language and compose. So and we can even iterate these constructions using fixed points to produce an n-controlled not function that takes a list of control bits and a target bit and flips the target bit if and only if all control bits are true. So we have the n-controlled not function here using the fixed point construction. So it's defined as usual. The language is also expressive enough to write conventional recursive and higher order programs. And we illustrate this expressiveness using the usual map operation that is very usual in functional programming, and that applies a function to all the elements of a list. So we have G, and then these functions apply G to the elements of the list. So these examples use fixed points, which are terminating in any finite context, that is functions that are structurally recursive. Here I have just an example of the map. So summarizing, so far we have a high-level reversible language, expressive enough. There is a reversible pattern matching with a syntax for circuits. There is the type constructors plus and times, and a generalized notion of control. Following circuit description languages like Quipper and Keywire, we add recursive types, the lists, which are defined as usual, using the types plus and times. Higher order on ISOs, ISO variables, boxes in circuits can be ISO variables, lambda abstractions, and application, fixed points, and operational semantics using substitution and unfolding. Termination, the fixed points are required to terminate on all inputs, and an ISO describes a bijective map on the sets of values. So now we want to turn the ISOs in unitary maps. So we want the quantum thing. So in the language present so far, an ISO WAROB describes a bijection between the set of closed values of type A and the set of closed values of type B. So the sets can be regarded as basis elements of some vector space. And as an example, consider an ISO W using three clauses, V1, double arrow V1 prime, V2 double arrow V2 prime, and V3 double arrow V3 prime. So this ISO can turn in we can turn it in a 0-1 matrix, considering that they are basis elements of some vector space. And here we have this is a classical ISO. We have one, just zeros or ones in the matrix. And the things that we can extend these clauses following the idea of seeing ISOs as unitaries and not only bijections on basis elements, as I showed in the matrix before. Basis elements of the input space. So we can generalize the clauses to complex linear combination of values on the right-hand side with the side condition that this matrix is unitary. So the matrix must be unitary. And we can use the combination of values in the right-hand side. So from classical reversible to quantum in the finite case. So we have linear combination of data as a side effect. Following what's done in the intuition is that there is an adjunction between finset and finvec, and following what's done in linear algebraic lambda-calculi, have A plus B as this is the way we define linear combination of terms using left U plus right V. So left U and right V must be orthogonal subspace. And in the finite case, we have finite dimensional space, and ISO U A double arrow B yields a unitary map A to B. We have superposition of clauses, so we add the constructions for superpositions, and preservation of orthogonality and norm. So here I have an example. So this allows us to define an ISO behaving as the Hadamard gate, or as like here is the ISO as the Hadamard, and as I said, the matrix must be unitary. The the construction of this matrix must be unitary, what I have here. And then I have a more complex ISO, the gate with conditionally apply Hadamard. So here's the definition, and following the same idea. So ISOs as unitary maps in L2, the standard L2 of the Hilbert space L2 of infinite sequence. So using recursive types, we consider lists such that A is infinite dimensional, and as the candidate model, we use the Hilbert space L2 of list of A. Space of converging sequence indexed with the lists of A. So we have unitary maps U that are surjective, that preserves the inner product, and they are bounded. So with enough conditions on fixed points, in this case the iterators, we have that this general ISOs, list of A's, double arrow, list of B, they yield unitaries as U1 in L2, list of A to L2 list of B. So here there is an example of a map Hadamard using the traditional map to apply Hadamard to a list of qubits. So the definition is using the fixed point operator. So we apply Hadamard as we defined before to all the elements of the list. So this is to show the expressiveness of the language, so that it's a simple notion of recursive construction, but we can use. So in this work, we propose a reversible language that's amenable to quantum superposition of values with quantum control. The novel aspect of quantum control that we are able to capture here is the notion of quantum loops in a simple way. And these loops are believed to be hard. And we use the simple iterators on lists, but still we have simple loops. And what makes it work in our approach is the fact that we are firmly reaching a closed quantum system without measurement. So we provide a generalized circuit construction language with the notion of quantum control. I think I was more fast than I hope, but I'm ending. So thank you very much. And sorry about my poor English.
Thank you, Juliana. Now the questions from the YouTube are arriving. Daniel Fortunato is asking, is the language already implemented? I was curious about that.
Not yet. I had a student, a master's student, that started to implement, and this I was studying the presentation, and I was thinking, we need to finish the implementation. He started, and he did more things for his master, but he didn't finish. And we don't have a PhD course in our university in computer science. So he went to other university and he started to do other work. So he couldn't finish. So this is it's a to-do very strong thing that we need to accomplish. Yeah.
You are looking
Thank you very much for the
operations.
And even we can now like implement it to run in QuizQuit and to run the algorithms in the IBM quantum computer. So we can do this backend for the implementation. I think we need to do that.
How hard is it to generate the code without a compiler, a proper compiler?
To generate the code without I think we can implement. He started to implement in Haskell the interpreter for the language they interpreted the language to circuits. So we can, I think it's even easier. So we can implement this interpretation of the language to circuits, and then we can try to run in using these libraries, for example, in the IBM Quantum.
Oh,
thank you.
Nice. I was wondering if you could comment also, because now there is a lot of talk about quantum AI. Artificial intelligence, and the people, when they think about artificial intelligence, they mostly think nowadays on machine learning. So I don't know if you have already started thinking on the possibility of learning the programs by examples.
Yes, this is a very interesting thing, because like everybody wants to work with quantum machine learning now. And I just started to study about quantum machine learning because the students want to know about that, and but I don't have experience programming the algorithms for quantum machine learning. I just studied a bit about the algorithms, but I think if we can implement the language, maybe we can experiment with some algorithms of quantum machine learning. And even I remember that when I was studying quantum machine learning, I started to use the IBM quantum experience. So if you can try to do that, yes.
Yeah, if you generate code for a machine that already has some insights or something done on learning how to generate, then your code could be adapted and combined. Pedro Diniz is apologizing for being a bit late, but he says that traditionally in quantum, if one can say that, there is the issue of redoubt being destructive. So how is this captured in his language, if at all? Alternatively, when the computation terminates, how is the result captured? Or is the language orthogonal to this issue?
Okay. Like for example, here, like in the map Hadamard, for example, the computation ends in the base case, like when we find the iterations of like we are using the recursive type of lists, and I don't know if I'm being clear. If I don't know if you understand the question. So the computation ends when we reach because the only way we have the loops is using these lists. So I don't know if you understand. Thank you very much for the question.
Pedro, if you have something more to say, to be clearer, please unmute yourself.
I am muted.
Yeah, I'm sorry. I was a little bit late. Yeah, I think I got it. Thank you, Juliana. Okay.
Okay.
I had another question, Min. Are you envisioning having a simulator as a starting point for this implementation of your language? I mean, I'm wondering how can people play with with your language, essentially try to get a feel for how do they map their problems using this language. I'm wondering if this is something that you have in mind.
Yes, yes. I think it's the better way is to implement the language.
Right.
Yes.
Right.
Yes.
Okay.
And so as I told you, I have a student that started implemented, but he didn't finish. So this is a project that I want to do.
Perfect. Okay.
Very soon.
Yes. Okay. Got it. Thank you.
Thank you.
Also, Rui Maranhão is telling us that they have, he and colleagues, I believe, have a paper coming comparing the efforts implementing quantum AI with QCT versus Circ. And QCT seems faster, easy and easier. And it says perhaps even faster with this language.
Mm-hmm. Yes.
So
thank you. Thank you very much. Yes.
Yeah. Any more questions? You said about simple recursion at the moment, simple loops.
Yes.
Do you see a problem, for example, that couldn't be modeled with these simple loops?
That couldn't?
Couldn't, yeah.
That couldn't. No, a model that couldn't be modeled, that couldn't be used with the simple loops.
A program that some kind of problem that you couldn't solve by stating the solution of the problem as with these simple loops.
Yes. I don't think. I don't think about that. Sorry. Sorry. Yes. Yes. I think they could be more general if for example with measurements. I think the problem is I think this is a very difficult point, that to deal with loops is the measurement, to work with open quantum systems. There is this I don't think we didn't find a model still to work with the open quantum systems. So algorithms with measurements and loops, maybe.
Okay.
I don't know.
There is another question coming. Is there any expected computational complexity improvement from the use of quantum control structures compared to quantum operations embedded in a classic flow control structure?
Yes.
Yes,
it's very interesting question, but we didn't work on that yet, on the analysis of complexity in this quantum control setting. So this is a point to work. Thank you.
I have one comment about the construction of a language. If you want to have a compiler and everything, my experience is that a lot of details emerged, because when we have the transformations,
Yes.
so but if you want to have a language with the full definition of a language, then there will be a lot of small details. But it's just a comment.
Yes. Yes.
Yeah.
Yes. Yes. If we actually, I tried to show in the presentation more the examples, but we have all the formal definition of the language, the types and the semantics. But yes, we have the definition. So, and even just to implement the interpreter, I start with the parser, and then it's a long way, the implementation of a language. Sure, it's a lot of details that started with the parsing, and then the syntax of the language, the types, and then yes, and then the semantics. So it's, so it's.
I'm not sure if I understood it correctly, but you said you have a limited or unlimited recursion.
Limited.
Limited.
Yes, limited. It's just it's just a structural recursion.
But you can have a potentially infinite recursion, or you have to have a limited depth in that recursion. Like
no, we can have the recursive types, the infinite recursive types that are bounded. So we have this, we need quantum termination. So there is no, I mean, there is no meaning for, still no meaning for an infinite quantum circuit.
Okay. Well, I'm not sure. I think, is there any other question coming from YouTube?
No, there are no further questions. So I guess if there are no further questions, we can stop now. And thanks, Juliana. Just a final announcement before we finish. So we'll have another talk in a month from now. You can see the details on the website. But for now, thank you, Juliana. It was very interesting.
Thank you. Thank you very much.
Thank you, Juliana.
Thank you.
Thanks a lot.
Thank you a lot, Priscilla.